We are going to continue with chapter 2. Now we are going to study wire resistors. We have so far variable resistors, which are the potentiometers. We have the ceramic resistors, which are the fixed value resistor, and now we have the wire resistors, which these ones are the ones you can make yourself by selecting a specific material with a specific length and a specific cross-sectional area. This is the formula. R represents the resistance or resistor. Is equals to rho, which stands for resistivity, the length of the wire you're going to be using, and the cross-sectional of that wire. So based on these parameters, you can pick the value that you want your resistor to be. So in the example, they are saying that what is the resistance of a 400 feet of 22 gauge copper wire? The area is 642 circular mils, and the resistivity of the copper is this. We have a table to find the resistivity of specific materials. So that resistivity gives us in 1,000 feet. In 1,000 feet per unit, so that we can use the formula to calculate which one it is. So they use it by proportionals, and they use it with the equations. So based on that, we have that this will be the resistivity, we have the length of the wire, and we have the cross-sectional area of it, so we can successfully find it. On the next, okay, this is important. Right here we are going to start defining what an electric circuit is. In other tutorials, I have done a simulation or a little tutorial of how to use the multisim for an electric circuit. And I said a little bit about it, but I didn't explain it. So here it is, the definition of an electric circuit. Something to be considered an electric circuit, it has to contain three things. It has to have a voltage source or a current source. It has to have a path, and that path has to be close. Current has to have to go back to where it started. And then it has to have a load. We cannot have a voltage and a wire go from positive to negative, and that's it. It will burn the voltage. So we have to have something that consumes that voltage, that goes through the path, and it does something on the load. This is a flashlight, and it explains that specific thing. So we have the batteries right here. So we have the batteries, which is equivalent to the voltage source. Then we have the pad right here. We have the path, and then we have the load, and the load is the light bulb. So the voltage comes here and it does something, and then it comes back to it with no voltage. Let's go to the next slide so you see what I mean by a closed path. So this is the picture representation of a circuit. So we have a closed path. So we have a beginning, and we go, and then we have the load, which is the lamp or the light bulb, and then we come and we close. So here, this is the schematic representation of a voltage source. So we have the bigger connection has the positive, and the smaller terminal, it has the negative. So we are going to say we go from positive to negative. So we say that the value of this battery is as 2 cells. So the cells can be 4 or 5 volts. We don't care. We say it's 2 cells. So these 2 cells are at this point. So what is the ground? The ground is connected at the negative. So we always assume that the negative is 0, and then the value of the voltage source is measured 0, 2 in this case, and then we consume those 2 cell values here, and when we go back, we have 0. A voltage cannot be 0 and another value at the same time. So if we have 2 here this lamp barely consumes 2. So when I get here, they are at 0 volts. It is important to know that we do these long lines here for understanding only, for just for that it doesn't look all messy. In reality, this point and that point, we assume that it is the same point. If it's not, nothing is connected between this point and that point, we assume that it is the same point. We just do it here so it is easy to see, it's visually pleasant for us to see it. And likewise, this point and that point, it is the same point. So we just say that this and that is the same point. However, this point and this point are not the same. Why? Because we have the lamp connected to it. So an electric circuit needs to have a power source, it has to have a closed path, it has to have a load, and it has to have a ground. Very important, very useful when you're going to be doing your labs. Switches. In this case, we have a switch connected here in the closed position, so it means current can go through it. So switches are like the light switches that turn on and off things. We have different types of switches. These are all mechanical switches. We have sensor switches which activate with motion, noise, different kinds, but these are how we have a single switch, a switch that can have 2 positions, a switch that can have the same position but control 2 different paths, or a switch that can go toggle between this point and that point. It all depends on the application of the switches. A multimeter. We have a digital multimeter. They are known as DMM. So a digital multimeter it's called a multimeter because we can take different measurements using the same equipment. So let me go ahead and explain to you how this works. So we have the position off, that's how we put it away. We have the leads, we have the red lead which represents the positive, and we have the black lead that represents the negative. Those are the standards, okay? So the black lead always stands connected to common, which is the ground. The red lead we can switch around. If we are going to measure voltage or current, you see the volt for voltage, and then we have the omega for resistor, then we connect here. And then we have to move to see which measurement we are going to take. So if we are going to take DC voltage, we will move to the V with a straight bar on top. That means we are measuring direct current, which is what DC stands for. If we are going to measure resistance, then we have to go to where the resistor is. In this case, it doesn't have anything, but it should have hidden ohm, and in that would be the position where you will put it at. If you're going to measure current, then we will have to unplug the lead from here and then connect either to the milliampere current range, or you will connect to the ampere current range, whichever it is that you're going to be handling. So in our case, we'll probably connect most likely to the milliamps, because that's the value of the current that we are going to be measuring. So you will move these two over here, and then you will move the knob to current, which would be right here. You see the A, that stands for amperes, and then we have the straight bar on top, so that stands for DC current. Okay,